Alright, so guys, we're starting Module 6, Electricity and Magnetism, and we're going to start right at the beginning. We're going to do some revision of terms you should know by now. So the first one being, you all know, it's terminology, it's all information you know, that all materials contain protons and electrons, because all materials are made up of atoms. Atoms are made up of protons and neutrons. Protons and electrons, sorry. When the number of protons, so my positive charges, are equal to my number of negative charges, then my object is neutral. You guys know that, all right? If there's an excess of electrons, then it's negative. If there's a deficiency of electrons, then it's positive. Remember, protons can't move, okay? Protons can't move. That's important. The unit of charge is, well, charge is Q. We measure charge as in coulombs. Now, please be careful here. Charge is one of those few little physical quantities that sometimes gets put as a big Q or a lowercase q. It all depends on the situation. So don't get worried about the fact that we can actually have it both as a uppercase and a lowercase. Now, the principle of conservation of charge, you've done lots. And then remember, that says to us that the net charge in an isolated system remains constant. Basically, what that means for us is we can't create or destroy charge. We can transfer charge, we can make it go from one object to another, but we can't make our own charge. Okay, there is a certain amount of charge in the universe, and we just transfer it from one place to another. Then there's a quantization of charge. Now, every single charge in the universe, and this has been proven, is an integer multiple of the electron charge. Now, the charge on an electron is minus 1,6 times 10 to the minus 19. Oh, that should be coulombs. It's very, very small. But anything that is charged, if you take the charge that it has and divide by this number, you must get a whole number, even if that whole number is ridiculously big. The smallest number you can get is 1. Now, you've done this equation before, and you might have seen it where it's NQ over QE. Now, QE stands for the charge on the electron, which is given to you on your information sheet. But here, I've put it as 1,6 because whether that's plus or minus all depends on what charge you have, because that is number of electrons, or it could be number of protons. Depends on whether you have more protons or electrons, but it's a number. It can only be a positive value. You can't have a minus number of electrons. Even if you're going, but what if there's extra electrons? That's fine. It's still a number. You can't have a negative number. This is a scalar quantity. It can only be positive, okay? Which also means when we do substitutions in these equations, this charge and that charge must have the same sign. So they must either both be positive or they must both be negative. And whether this one is positive or negative depends on the charge you're working with, okay? That's the important thing. And then just to remind you, like charges repel, unlike charges attract. You know this. So, having done some revision and a little bit of stuff you should know, now we need to talk about Coulomb's law. This is where we start the new work, okay? So, first of all, we're going to look at the electrostatic force between 2 point charges, and we're going to look at how they're directly proportional to the product of the charges. Watch what we're going to do. So here we have two neutral objects. Sorry, that one's not quite neutral. Now it's neutral. If you look carefully, they're both experiencing zero force. I'm going to make one positive and the other one plus. First of all, I want you to take note is that, and I can't write on this app, I'm sorry guys, that both of them have the same force, 22,469 newtons. Why? Because of Newton's third law. Okay? If one is exerting a force of 22,469 on the other, then the other is experiencing the same force when object A exerts a force on object B, object B exerts the same force and magnitude of the same force, but in opposite directions on object A. Alright, so now we've got a force of 22,469. If I double one of the charges, I've doubled the force between them. If I double the other charge, they are now 4 times bigger than it was the first time, because I've doubled both charges. So what we're seeing from this is if I make the charges bigger, the force gets bigger. Okay, now here the arrows are pointing upwards because these are both the same charges. They're both positive charges. If I turn that to -4, it's the same value. 359, watch. 359. Same value, just in opposite directions. So if they're both the same, there'll be a repulsion. If they're both different, then they are attraction. So, directly proportional to, and what I just want you to add in here, that should be to the product of the magnitude of the charges. Okay, we only look at them as positives. We don't look at the negatives. Okay, so Q1 and Q2 are a certain distance apart. They experience a force of F. If I double one of the Q's, that F becomes 2F. If I double both of them, it now becomes 4F. So it's about multiplying the value of this charge with the value of that charge. So force directly proportional to F to Q1 times Q2. So when I draw a graph of this, because it's directly proportional, we recognize that we have to get a straight line from the origin. Has to go from the origin. Now, we're going to look at what happens with the distance. So we're going to go back to this. I'm going to keep it as 4. Currently, if you look at my distances, they are 2 centimeters away from each other. Okay? Now, I'm going to double that distance. So I'm going to make them 4 centimeters. I'm going to move the blue one to 8. There we go. Now it's 4. So take note of the numbers. So here, there's 359. Now, I'm going to double that distance to 8. And if you take out your calculators and you go, the force we just had divided by this, you're going to see that it's 4 times smaller. If I now triple, so it was originally 2 centimeters, now I'm going to make it 6 centimeters. This is now 9 times smaller than the original. 9 times. So what you need to see is that the factor is a square. It's not just double. It's not just 3 times. It's 4 times smaller and 9 times smaller. That gives us this proportionality. So the force is inversely proportional to the square of the distance. When I have Q1 and Q2, force F between them. I double the distance, they now are a quarter. This is the same as 1/4 of the original F. If I make the distance 3 times, it's 0.11, which is 1/9 of the original force. So, force is directly proportional to the inverse of R squared. In other words, inversely proportional to R. When I draw a graph, it's going to give me a curve. This graph does not prove that they're inversely proportional. This just simply tells me that if the distance increases, force gets smaller, and it happens to be with R squared. To prove that it's inversely proportional, I need to draw a straight line graph. So I need to draw a graph of the inverse of 1/R squared. That graph must go through the origin. You've seen this lots now. We did it in Newton's law of universal gravitation, and you saw this when we do Newton's second law. So now, force directly proportional to the product of the charges. And our force is inversely proportional to the square of the distance. If we combine these proportionalities together, we get this. This is an expression. We can't do calculations with it. To get rid of that proportionality, we need a constant. Now, that constant's been worked out through drawing graphs, through calculations. You don't need to worry about how we get there. But that constant happens to be K. By introducing this constant, I can now have an equal. That means I've got an equation. I can do calculations. F stands for force. K is Coulomb's constant, which is 9 times 10 to the 9. It's a big constant. Q1 and Q2 are charged, must be in coulombs. And R is the distance, must be in meters. We're not going to work with kilometers for this, because then the force is way too small. But we may work with millimeters or micrometers or nanometers. Same with coulombs, milli, micro, nano, coulombs, etc. So that gives us Coulomb's law as a statement. The magnitude, so this doesn't tell me direction, we'll deal with that later, of the electrostatic force exerted by 2-point charges on each other is directly proportional to the product of the magnitudes of the charges and inversely proportional, not indirectly, inversely proportional to the square of the distance between them. This looks a lot like Newton's law of universal gravitation, but remember, there must be no mass in it. This is about charges, okay? Now remember, milli, if I have millicoulombs, I'm going to go times by 10 to the minus 3 to get it into coulombs. Micro times 10 to the 1 times 10 to the minus 6. And we write, it's like a U backwards, basically, with a long tail on the left instead of the right. Nano, minus 9. Pico, minus 12. You must make sure you recognize the symbol, first of all, and you can do the conversions, because remember, we only work in coulombs and we only work in meters. Quick reminder, last thing. When two objects are brought into contact with each other, the charge on those objects will be distributed evenly. Charge likes to be as far away from each other as possible. Charge likes to try and neutralize the objects if it can. What that means for us is when we touch two objects together and then move them apart, both those objects will have the same charge. You've done this before. We have this equation where Q nu is Q1 plus Q2 over 2. Here, whether we've got a positive or a negative is actually very important. So, the sign is important. We can't leave the signs out. We can't leave the signs out. In any other equation that we do in electrostatics, you leave the sign of the charge out. We're working with the magnitude of the charges. Here, no, because we're looking at how the positive and negative neutralize themselves. So, that's where we're going to stop for now. In the next video, we'll do some calculations. We'll apply we will apply Coulomb's law. Oopsie.